we proceed to debris flows and multiple consecutive searches. It will be described the wave pattern and hence also an input for debris flow models and design for mitigation measures. It will be presented by Tobias Schöffl. He is a researcher at the Institute of Mountain Risk Engineering at the BOKU University in Vienna. He is currently in the final stage of the PhD program, Hazards and Risks in Alpine Regions Under Global Change. The focus of his research is the investigation of natural debris flows applying a pulsed Doppler radar. Please.
Thank you, and thank you also for the opportunity to present my research here. Would say let's dive right in. Debris flows are one of the most destructive geophysical, gravity-driven processes in mountainous areas, and they are reported to give rise to waves resembling those found in shallow, granular, free surface flows under laboratory conditions. These studies also report that wave coarsening can produce high amplitude waveforms, indicating that the origin of the most destructive parts of debris flows may lie within these wave phenomena. If these findings hold true for natural debris flows, it could significantly increase the risk for mitigation measures and ultimately endanger alpine communities and infrastructure. Without continuous high-resolution measurements, especially for events consisting of several successive waves, the subsequent dynamics or volume estimations, which are paramount for the calibration or the development of new debris flow models, are somehow subject to speculation. To investigate natural debris flows, our institute operates a monitoring site at the Gadria Creek, located at the Alto Adige region in South Tyrol in the eastern Italian Alps. And here the catchment covers an area about 6.3 square kilometers and is one of the few in Europe that regularly delivers natural debris flows once or twice a year, always triggered by heavy convective rainfall events during the summer months. And therefore, a monitoring barrier was built in 2016, followed by the installation of a pulsed Doppler radar, or short PD radar, in 2017, which is directly mounted on the filter check dam. In this overview map, you can see the coverage of the radar beam over the torrent channel, and to achieve spatial resolution, the radar transmits pulsed electromagnetic packages at discrete times, which results in so-called range gates or resolution cells. And for this study, we set a length of a range gate to 25 meters. And in addition, radar from flow height sensors installed directly on the monitoring barrier in range gate 5 and on a wire cable system installed by our Italian colleagues in range gate 6 are used for this research. Now, within each range gate, surface velocities are derived by utilizing the Doppler effect, and after time discretely matching the echo signal, we obtain 4 Doppler spectra every second, and a single Doppler spectra consists or has a resolution, consists of classes which have a resolution of 0.058 meters per second per class, for a total of 1,024 classes. And within each class, the amplitude of the echo intensity or power signal indicates which velocity classes correspond to moving parts on the surface of an incoming flow. An example of a plotted time series of these Doppler spectra results in so-called Doppler images and can be seen in the upper part of this slide. And to further estimate that discharge, we derive a median velocity value of the Doppler spectra at a depth averaged coefficient termed B and then multiplied by the corresponding cross-sectional area. And as the cumulative echo intensity is a really sound indicator for large objects passing through the channel, or in the large objects are in our case, of course, the waves which pass through the channel, we further use this value for wave propagation analysis. Now in 2020, we encountered 3 severe debris flows within a 10-day window on the 2nd and 10th and 12th of August, each of which exhibited significant parts with a very homogeneous wave pattern, as can be observed in this corresponding discharge hydrographs. And for debris flow 02, which is an abbreviation for the first debris flow, the integrated volume was around 16,000 cubic meters, for the second 20,000 cubic meters, and for the last one 13,500 cubic meters. And interestingly, we find the highest discharge values of around 100 cubic meters per second for all events right before the wave cycle was initiated. Now, in this short clip, you can watch a single wave passing through range gate 5, and to scale this monitoring barrier here is 2.5 meters high. And a closer look at the wave metrics reveals a really striking similarity. As highlighted in this box plot, where the edges of the boxes represent the lower and upper quartiles, the center line marks the median, and the whisker mark the lower 5 and upper 95 percentiles. We find that the highest wave volumes are at the front, as highlighted in this box plot. And we further note that the time between waves is again found to be in a very narrow time frame. In average, every 23 to 27 seconds, a wave approaches. As mentioned earlier, we utilize the cumulative echo intensity to further calculate propagation velocities, and to do so, I tracked each wave from each debris flow from range gate 9 down to range gate 7 and down to range gate 5. And the results, again shown here as box plots, show that the wave metric of propagation velocity is really consistent, with median values ranging around 6 meters per second. Now let's take a closer look at significant sections. In this plot, the Doppler velocities are assigned to the left y-axis, and the echo intensity is plotted as a color scale, as so-called Doppler images, and the evolution of the flow height is assigned to the right y-axis, and the median velocities are shown in orange. And when we focus on the first few seconds of this plot, here a slow incoming granular front stops for about 50 seconds and is then remobilized by a following high amplitude and high velocity wave. And after this wave has passed, the erosion deposition wave cycle is initiated. And what is really remarkable about this phenomena are the completely stationary parts in between the waves, where debris is deposited up to 1 meter high and then remobilized by the following waves. In this next short clip, you can observe the arrival of a very violent front from in range gate 5 with propagation velocities up to 10 meters per second and flow heights up to or over 2.5 meters. And as you can see, this caused a huge run-up on the monitoring barrier, in turn destroying our flow height sensors and also blocking the radar signal for a short time above range gate 5. And in the plot below, you can see the Doppler image from range gate 6, and here you can also observe the collapse of the radar signal. And what is also really remarkable about this is that within 15 seconds, approximately 800 cubic meters passed through the channel. In this last video that I'm going to show you, you can observe another granular front, this time from the second debris flow, and the front is overflown and significantly coarsened and amplified, and this motion of flow behavior is also evident in our radar measurements. In this range time intensity velocity plot, all the median velocities from range gate 1 to 10 are assigned to a color scale, and the echo intensity is assigned to the z-axis. And here the first high velocity wave, which represents the granular front, slows down and gets then overflown and coarsened by a second wave. And within 40 seconds, about 1,200 cubic meters were transported. It appears that with modern monitoring systems, such PD radar waves within debris flows become more apparent and are not as rare as might be expected. Consequently, this challenges most existing debris flow models, and it is essential to consider this when designing mitigation measures. Our observations at the Gardrier Creek show that a fairly high discharge of about 100 cubic meters per second seems to be required for the waves to develop, and once the flow breaks down into a series of waves, not only do the wave metrics show remarkable consistency, but it appears that the wave pattern dominates the flow until their end. A quick acknowledgement. Really would like to thank IPTB BOKU for the installation of the PD reader, and also, like mentioned before, our Italian colleagues which helped us construct the monitoring barrier. Thank you.
Thank you very much for this presentation that also highlights how practice, in this sense, detection systems can also really help to advance in science. We don't have a lot of time for questions, but allow me one quick comment or question.
Yes.
Can you translate to the audience a little bit what the difference, do you see a general pattern between how the front moves and how your waves or surges move? So what is the most dangerous part? You did a PhD and now you have to tell the audience, is the front the dangerous part, or is it the surges, or is it the waves?
I mean, it appears, at least for one of the debris flows, that it is a mixture, because at the front there are big boulders to be found, and but because of that the front tends to move slower. But with those waves overtaking the front, it can be significantly coarsened, and therefore I think a mixture of both are really the most dangerous part, I guess.
So velocity is not everything. Thank you.